Hey guys, this is Michael. Welcome back to Hardware Engineering. So this problem here, the complements problem, I solved this problem yesterday, and I was very excited about it. And I came back in here and I tried to load my saved circuit. It seems okay. So it's an alpha product. Bear that in mind. There will be fixes, but right now this thing doesn't save circuits worth a darn. If you leave the tutorial, come back to it, your circuit will be all sort of disconnected and wires going everywhere. I haven't been able to actually save a circuit properly, so I don't quite know. I saved the circuit that worked, but I don't quite know how to rebuild it because it doesn't seem to be working in the way that I thought it worked. The way I sort of thought I solved it was looking here at the tasks and hints. It's a lot simpler than I was making it, right? We're not actually supposed to be doing the whole, carry in of a high and blah, 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 blah. It says a 4-bit input A will be given. Find a number B such that A plus B equals 0 and assign it to the output O. Now, that means that all we need to do is find B, not the whole thing, not the addition, but actually just B, which is the ones complement of A, which is input A with a not applied to it. So in theory, this here should work. Now, I can't remember whether this is the circuit I got to work or not, but I haven't been able to get it to work again, and I can't tell if it's because this is, this may not be the circuit, right? There may have been something else. I honestly cannot remember, but I can't get it to work again. I did this on my laptop and whatever. I'm going to skip this because, yeah, forget about it. We're going to quit this tutorial, and we're going to proceed onward here because I want to keep going, and it doesn't really matter because we're getting in this subtraction problem here. We're going to get an actual subtractor logic gate. But suffice it to say, the lesson taught there is that if we take a number, a binary number, and we apply, if we invert it, then if we add that number to the original number, the result will be ones all the way across. And then if we flip that again, then we get 0, essentially. That's the way we're creating a fake negative number in binary. So what it says here is, under subtraction, we could surely build a new truth table and try to face the problem of subtraction by elementary means, but we leave that as an exercise to you and as a catastrophe for your sandbox. Equipped with the wisdom of elderly, we can cease the fact that A minus B equals A plus minus B for our own good. Again, the minus B being the negated A. You'll surely notice that having two adders for negation and for the addition itself, one of which is actually used for adding 1 padded with zeros, may not be the best way to go, but a full adder is known to have a carry in, which we haven't been using much until now. Adding 1 to an already working addition of two inputs, A and not B, has never been easier. So we're supposed to design a circuit that subtracts B from A while putting the result of subtraction to O. A is the minuend, B is the subtrahend, and O is the difference. And that's all we've got here. So we've got input A, we've got input B, probably going to want a little more room there, and we've got output O over here. And we might need a ground, and we might need a high. So let's grab those. And I believe we're going to need this 4-bit NOT gate. And I feel like we're going to need another NOT gate, but let's come back to that in a minute and see if we do. I'm not real sure. And then we have... So here's where we're doing the thing that I wanted to do to begin with. I think that if we take these guys, wire this up through a knot, put them into here, put the high here, put this here. Here, I'm just going to hook these up like super quick so that we don't have to jerk around with it. And then connect these guys up. I think this is going to solve this problem, but let me go offline and wire that real quick. Okay, back with the finished circuit, and we're just going to see if it works. If it doesn't work, then I don't know. I don't know the answer, man. Okay, let's see. Okay, Step 2 worked. That's encouraging. Step 3 worked. Step 4 worked. Step 5 worked. 6. And 7. So we passed this. And this is the circuit I was trying to build before, but as you can see, we didn't really need to do all of that. We just needed to find the complement, I think, of the thing. And I don't know why I couldn't get that circuit working, but I'm not even gonna look back. I'm not gonna worry about it now, because I don't think we have to care. So we're going on now to multiplexing. And multiplexing is putting data out from multiple inputs if we have a certain thing selected. So here's the little symbol of their multiplexer, right? So we got A and B in, C out, and S as a select line. And it goes, that's essentially what it goes through. Step by step we proceeded through logic, blah, blah, blah. We now need to learn about storing information to possess all the tools for designing a CPU on our own. All right, so let's get a grid. And let's look at what it says. Draw a circuit of a device that takes two numbers as inputs, performs both addition and subtraction, and lets user decide, using a select line, which results to forward as output. And we have inputs of A, a 4-bit number, B, a 4-bit number, select, a 1-bit select line, if 0, addition, otherwise subtraction, and O is the 4-bit output of nature depending on select. Okay, so here's our input A. Here's our input B, and here is our select line, which we will probably actually have up here. And then we have our output here. We're probably going to need a ground for the carry out, and we're probably going to need a high for the carry in if we're doing subtraction. All right, let's see what else we need here. I do think we're going to need a 4-bit NOT gate. We're definitely going to need these multiplexers. Now these multiplexers are one line in with a select, or 2 lines in with a select in as well. So we're going to need, I think, 4 of these guys to do this problem, because we're going to have to select between each of these, right? We're going to have 2 outputs, and we're going to have to select each line and put them into one line, and then that is going to go into here. So our layout will be like this. We're going to have, you know, that guy inputting right there, but we'll move it over a little bit so that we can fit them all. And actually, we're probably going to, for clarity's sake, move these down a bit so that they're not overlapping, so that we can hook them up sort of in a sane way. Maybe like that. Is that going to cause us any problems? No, we should be all right with that. So you through there, you guys through, yeah, we should be okay. We should be okay with hooking that up. So we're going to hook up D to these guys. We're going to hook up the select line to these guys right here. And then we're going to do our addition, subtraction business over here. So let me try to get back to gates, because logic gates, because we're going to need them. We're going to need a full half adder, a full adder, and I guess that's all we get. Is that all we get to work with? Really? Now I'm confused on how this will work, because I thought we would need like 2 of these, one to do the addition, one to do the subtraction. No, all right, well then maybe the multiplexers are going to have to go down here and choose whether to... this could be a problem. I'm not sure I fully understand. Let me go and see if I can just take a look through here and see what's up. Oh, you know, never mind. I bet what the problem is that we can't get it because we have too many gadgets here. So what gadgets can we get rid of? I think we can probably get rid of this guy. Yeah, if we get rid of that guy, we can get another one of these. So I think we can take a half adder to do the actual addition, a full adder to do the subtraction. So let me go wire this up. Again, the muxes are going to go up here. Now I've taken them all out of order, but I'll put them back. We're going to have the knot sitting here, and we're going to take lines from B into there, and then up into the subtractor thing. We're going to bring A up into here. And then we're going to draw lines out before the knot into here, and over here up into there, right? We're going to put the high into here, and then we're going to take these lines and run them into the multiplexers, and then we're going to select them with this line, and then the output is going to come here to this guy. I think that's going to work. So let me go wire it up, and I'll be back in a little bit. Alright guys, here's the circuit as I think it will work. Don't know if it will. Here's A, here's B. We're taking the output of B, putting it into this adder over here. We're bringing the output of A into this adder, and we're putting it up here under the left side of this multiplexer. So when this is 0, I guess, it'll select the first lines and put them up to D. Otherwise, we're taking A, putting it into this adder, and we're taking B, inverting it, putting it into this adder. We're putting in a 1 here, and so we should, in theory, be getting the subtraction of those two numbers, and those are going into the second line of the multiplexers, which will be selected when this is 1, and we'll get the output here. Will it work? I don't know. Let's see. Okay, that one worked. 0 from 0 is 0, or no, 0 plus 0 is 0. Okay, all ones plus all ones subtracted is 0. Okay, that one worked. I'm not going to try to do though. It would be easiest to convert this to digital or to decimal, and then try to do the math, but I'm not going to bother. So that worked. That worked. That worked. Test 8 of 8. That worked as well. All right. Now let's go back to the circuit and take a look at it. Now I'll tell you, it's a certain. We got a budget here, right? A component budget, and they're not giving us enough component budget, which means I might have built this circuit too complicated. But they're not giving us a component budget to dispose of the outputs here, which we're not doing anything with. And any kind of circuit code, anything related to computers or machinery, you don't want to just have things dangling out here. I suppose it applies to real machinery too. You don't want to have some gear that's just turning and doesn't do anything, right? You want to get rid of that. So ideally we would have this going to the ground output, but we can't do that because I don't have enough parts. Again, maybe I've done it in a not like optimal way. Maybe there's a part in here that we could have used that would have made things different. I don't know. Maybe there's a 4 multiplexer that we could have used. It's possible. It's possible. Well, what if I get rid of that, select line, and let's see if there's like a better multiplexer. It's a 4-bit. Oh, geez, there's a 4-bit subtractor. Would that have done it for us? I think it probably would have actually. Let's delete that, and slip you in there. We're still leaving that line low, unfortunately. What's this? A 4-bit negator. Alright, let me delete this here. Do we get anything else? Is there a 4-bit subtractor without a borrow in? Yeah, I don't see it. Well, in theory, if we put our multiplex line back, select line back on, we should be able to run this and it ought to work. Let's try. Okay, first one works. That one didn't work. Huh. Hey, you got me, man. I don't know. Oh, because if we're going to do it, we don't need to negate. Right? I believe so. Let's go back. First of all, let me grab this ground line, because if I'm right, we'll want it to be there. And then let's go back and grab this subtractor. Where the deuce? Man, devs, if you happen to watch this video, I tell you, being able to put the being able to have these on a tab would be so much nicer than current. Okay, this line is going to give us problems when we try to connect. So let me just pop these down here like that, and then we'll connect this over to here. Is this going to work? Now we still have dangling outputs, unfortunately, but I think we have some more components we can use now. So let's try this. Does this work? Okay, first one works. Second one works. Third one works. Fourth one works. Fifth one. Sixth one. Seventh one. Eighth one. Okay, those all worked. That's pretty awesome. So, in theory then, now let's go back to the circuit. I kind of wish it wouldn't dim you out there. If we were to okay, we only get one ground, so that's fine. If we connect this over to here like that, there we've got our ground, and then I guess we could just take an input low and connect it here. If it still works, then I think this is a better circuit than the thing we were looking at before, because now we don't have any dangling lines. I mean, in theory, even though that was working, right, because we weren't doing anything with it, in theory, anytime you have something that's just dangling like that, it's undefined, which is not a thing you want when you're talking about engineering, where you want to know what every single part is doing at every single time. Same thing in code. You don't want to have just define some variable and then not use it, and that's why your compiler will give you a warning. So anyway, that is the end of that. I think we're only going to do one more episode of this unless you guys really want it, but next time we will get on to sequential logic. And here's where we're going to start messing around with flip-flops and things like that. So in digital circuit theory, sequential logic is a type of logic whose output depends not only on the present value of its input signals, but on the sequence of past inputs, the input history. This is in contrast to combinational logic, whose output is a function of only the present input. And so we're probably going to go through talking about latches, which is capable of preserving data. And I thought it said there were 3 pages. Now, my eyesight is pretty poor, I guess. So what are we supposed to be doing? You're going to develop a gear control for a civil aircraft. It's known that aircraft gear can be either up or down, so your gear control needs to be able to, 1, lift the gear if it's down, put down the gear if it's up. Prevent gear manipulation when the systems are locked. If you feel like it, you can do the whole circuit without using the newly provided components. Yeah, not likely. Put gear down is 1 when putting down the gear is requested before landing. Lift gear up is 1 when lifting the gear up is requested after takeoff. Systems locked is 1 when lifting and putting the gear down should not be allowed. Although not a listed input, internal status must be used for correct results when it is 0 when gear is down, 1 when gear is up. Gear up is 1 when gear is up. The following truth table is going to be something we haven't had here before. It is actually a sequence of inputs, each one depending on the previous, as true for sequential logic. And therefore, truth tables for sequential logic are from now on going to be referred to as input sequence. Another input sequence with internal state listed as input is 2 pages on from here. Ooh, okay, whatever. Not sure I understood all those words. Initial state, gear down, comma, internal state equals 0. Yeah, okay, so we'll take a look at this next time around. Landing gear simulation. So, again, I don't seem to be able to save circuits, so it's very unlikely I'm going to be like build the thing, save it, and come back and show you guys. So I'm probably just going to build it, understand it, and come back, and we'll build it on camera. But until then, guys, thanks for joining me, and I will see you soon. Bye.